Hello guys, welcome to Backbencher Studies channel. In the last video, we have discussed about the second order system and we already derived the overall transfer function for this second order system, which is being shown over here, which is omega n square divided by s square plus 2 delta omega ns plus omega n square. So based on this value of delta and omega n, based on different values of this delta over here, we can have different kinds of roots. So the roots of this characteristic equation is dependent on this damping factor delta over here. If we apply a unit step signal to this second order system, this second order closed loop system, then what will be the output? The output will be of different types based on this value of delta over here, which is the damping constant. So let me define what is this damping constant. So we already saw that based on our input in the first order system, based on our input, the output will tend to reach the input signal. We already saw that based on graphs. So that that is called the reaching of steady state value. So upon reaching the steady state value, based on the system configurations, it may not reach this steady state value. It may uh, kind of oscillate about this steady state value. So that is being represented by this delta over here, which is the damping constant. So it will damp these oscillations while reaching this steady state error. So steady state value. So that we will discuss in next classes. So let us have the output value when this unit step signal is being applied to the second order system and when there is no damping. There is no damping in the sense we can substitute the value of this delta is equal to 0 in this equation. So if we substitute the value of delta is equal to 0 in this transfer function equation, we can have this equation omega n square by s square plus omega n square. So if we substitute this r of s is equal to 1 by s, as we are giving a unit step input to the second order system, if we do that, then we can find out the output Laplace transform equation that is being shown over here. So this is the output Laplace transform equation when the unit step signal is being applied. So so if we if we apply the inverse Laplace transform to this signal, we can say, so the inverse Laplace transform of a sinusoidal signal sine of at is equal to, so if we apply Laplace transform to sine of at, we can have the a by s square plus a square in the Laplace domain. So this is similar to this sine of at over here. So if we take out this omega n outside, and what we have is omega n by s square plus omega n square, then if we apply inverse Laplace transform to this, we can have sine of omega n t into omega n we have in time domain. So and we have 1 by s over here. So remember, the integration in time domain is what is called is what is called division with s in frequency domain. So if we integrate this corresponding signal, which is omega n into sine of omega nt with respect to time, then we can have this output. So if we integrate this integration of 0 to t omega n sine of omega n t. If we do that, then we can have the output as 1 minus cos of omega n t u of t. So this is the output when there is no damping in the system. So this we can represent using a graph. So 1 minus cos of omega n t does not have any damping. We can observe that. So this is kind of oscillatory behavior in this system. The output is kind of oscillating with continuous natural frequency omega n, but it is not, the value of this output signal is not decaying exponentially. So if we have damping equal to 0, we can have the oscillatory behavior. And if we have the delta is equal to 1, then we can, what we can have is the critical damping case. So if we substitute this delta equal to 1 in the overall transfer function equation, then we can have this delta is equal to 1 is eliminated over here. So if we see this, then we have the kind of formula which is a square plus 2ab plus b square, which is the a plus b whole square. So we can write this as a plus b whole square kind of thing. And if we substitute R of S equal to 1 by S over here, we have the output equation as, so if we kind of solve this output equation in which is in Laplace domain by using the, so when we have this delta is equal to 1, if we substitute this delta is equal to 1 and thereby simplifying this in terms of a perfect square, and if we simplify this with the help of the partial fraction expansion, what we have the output equation as 1 by s minus 1 by s plus the omega n minus omega n by s plus omega n whole square. So if we apply inverse Laplace transform to this equation, we have the inverse Laplace transform of 1 by s as 1 over here, 1 into u of t, and 1 by s plus a. The inverse Laplace transform is, we already saw that, e power minus at. So here a is equal to omega n. So e power minus omega nt over here. And if we so do this inverse Laplace transform, we have the 1 by s square inverse Laplace transform as t power 1. So t power 1. So if we kind of shift that with an exponent of frequency omega n, we can have this kind of Laplace domain equation. So we can, if we apply inverse Laplace transform to this by applying the shifting property of this inverse Laplace transform, we can have omega n t into e power minus omega n t u of t. So this is the output when this zeta is equal to, or this delta is equal to 1, which is the damping equal to 1. So this will become the output. If we observe that here we have the decaying exponentials. So here we don't have any oscillations in the steady state. So we can have this damping over here. We can observe this damping over here. So this is this up to this only today. So in the next lecture, we will be solving if this delta value is lying between 0 to 1, how we can solve that. That will be the general case. Then in that expression, we can have this delta in the output equation expression. So thank you guys. Thank you for your amazing time.